All right, this is for the millions of Twitch fans out there. Thanks for the 100 bits. No Mason today. Where's Mr. Mason? He didn't send you streaks, bro? Okay. All right, guys, we're going to discuss something that you may have seen before. April, let's put the thing away. So the question is, if you were to graph this function, what would it look like? So when you graph something, there's typically a y-axis and an x-axis. Now this part is can be confusing because when you have a statement like this, what kind of quantity is x if you're taking the sine of it? What do we take the sine of? Angles. So x refers to some angle on the unit circle, and y is the sine of that angle. Okay. Now you can see why that would be confusing because you're like, well, oh man, I usually on the unit circle I associate the x values with cosine and the y values with sine. So you kind of have to like break away from that a little bit to understand this. So let me give you an example. Here's the unit circle. This first position, what angle is that? 0 radians. So this position, I can talk about this position like I'm interested in the sine value. So I might write something like the sine of 0 is equal to 0, right? Now, since I'm trying to graph it, this 0 is my x value, and this 0 is my y value on this graph. So right there like that. All right? We're done. That's the whole graph. Just kidding.
wish.
Now, what's going to happen as we increase our x value? So increasing your x value is like moving counterclockwise around the unit circle, right? So let's talk about what happens when you hit here. Yeah, the sine of pi over 2 is 1. So which of those numbers is the x value and which one's the y value?
Pi over 2 is the x.
How do we feel so far?
Makes sense.
So on this graph, when x is pi over 2, the y value is 1. So I'm going to put that point right there. So right now we just have two. Now, could I have looked over here and gone like, oh, the sine of, say, pi over 6 is 1/2, and put that point on the graph? We could have. I mean, while I'm there, I mean, that point would have been somewhere like there, right? So let's keep moving. This point, keep moving counterclockwise. This point is the sine of pi is 0. Still making sense or no? Okay, so I've got, yeah, so the sine graph goes up and then down. Let's keep moving. What's the sine value down here?
Down further.
Sine of 3 pi over 2 is -1, so that's my x value. 3 pi over 2 is -1. Any questions still? And then let's come back to where we started. So this point could have also been described as talking about the sine of 2 pi equaling 0. So 2 pi Gets me 0. Now, time for our favorite activity. Connect the dots. Do you think the dots get connected with jagged, straight lines or with nice, smooth lines?
Smooth brain.
Lines. Smooth brain.
Oh, that's beautiful.
What? Okay. Now, is that the whole graph?
No, it goes negative.
No, not only negative, but I mean, couldn't I just keep going? I could go, I hit 2 pi, but nothing stopped me from just going more and more and more around the circle. Okay. So if I zoomed out, for example, I would have, this would just cycle around infinitely many times. And then on the left side, suppose I move to a negative angle. Do I get negative sign values or positive sign values if I had gone in the negative angle direction? Negative. So what that tells me is that this graph would go kind of like that. Okay? This is the zoomed out version. So, okay. No questions? We sure? No confusion? What is the domain of this function? All real numbers. Because you can go around the circle as many times as you want in the positive direction, and you can go around the circle as many times as you want in the negative direction. So the radian value that you plug in here could be any number. However, the range is just, here's a hint. What's the range? -1 to 1. Cool? Period. Period. That's a word that just means how far horizontally on the graph do you have to span before you get one full cycle of the graph.
0 to 5.
And then you just say, so 2 pi is that distance. So from here, this is one cycle. That horizontal distance is 2 pi. That's 1 period. And if you think about it, that's the same distance as going from, like, say, a peak to a peak. You could have also done that distance too. Right? Now, I hope that makes sense with your understanding of the circle, right? To go fully around the circle is 2 pi radians, so that's 1 period of the process. No questions? All right, it's cosine time. By Nikita. It's cosine time.
Cosecant.
I'm still thinking about the small one.
Huh?
I'm still thinking about the small
The
one.
small one.
They're so cute. Things I shouldn't care. I can show you.
I really liked how that game didn't try to have like a story where it had like an optional story. You could go read about it if you really wanted to, but it always bugs me in games when it's like you're trying to shoot some aliens and it's like, oh, it's a cutscene where there's some wizard or something. You're like, bruh.
Oh no, I still don't know what's going on in the story. I just know that they're small.
Yeah, small one. Okay, cosine time. Now, that's what we were talking about, yeah. She was talking about there's these new little baby versions of some of the bad guys. They're these little adorable, like swaddled, like
Smallin.
Smallin. The bad guys were called Fallen, and now they're this little ones are called Smallin.
Well, that's what the community named them. I think they're just called like children of fallen or something. I don't know.
Well, I really liked Halo back in the day, like Halo 2 and stuff.
Oh.
I didn't even realize there was a story to that. I would skip through all the story parts. So later on, people would be like, "Oh man, I love the story of that game." And I'm like, "There's a story? Oh, just a bunch of lizards I was supposed to shoot or something."
I played that video game, Mr. Hall.
Really?
Yeah.
Yeah, thanks. On the original Xbox?
Yep.
Back in the glory days before you needed an internet connection to play any game. Okay. Cosine time. So we're going to do the same journey around the circle, right? So we're going to go from 0 to 2 pi. In fact, let's go ahead and label these right now. So it makes sense where we're going to hit the same exact numbers, like the same values are all the same important values that we want to really focus on. But this first point that we start at, the statement that we're going to write to talk about this function would be the cosine of 0 equals, what's the cosine of 0?
0.
1. Cosine of 0 is 1. Okay. So the first point on the graph is up here. Well, first in quotation marks. That's the y-intercept, to be more precise. Now, what happens to our cosine values as we travel around the circle?
Smaller.
They get smaller. Right here.
Yeah.
So cosine of pi, until you hit cosine of pi over 2, your cosine here is 0. So at pi over half a pi, you've hit your first x-intercept, 0. Interpretive dance. Okay, just add some flair, you know. Okay, now, what kind of numbers do we have for our cosines in this neighborhood? Negative numbers. In fact, they're going to be negative all the way until we get to 3 pi over 2, right? So let's pit stop here. The cosine of pi is -1. Let's put that on here. And the cosine of 3 pi over 2. They're still negative in this neighborhood. Negative cosines, negative cosines, negative cosines until you hit here, until you get back to 0. And then you keep traveling. Eventually you get back to the cosine of 2 pi, which is 1 again, back to where we started. How do we feel about that?
Good.
And then what kind of pointy or smooth? It's actually going to be pointy this time. Believe it or not. No, I'm just kidding. Just lying. Magically, it's actually a really interesting function out there. It's the pointiest function of all time. Anyway, learn about it next year. I can tell you about it. It's like so in calculus, you're really concerned with pointy things. It's a thing. It's related to something about differentiability, but like a function like this. Oh, you guys know a pointy function. You guys know a couple actually.
Absolute value.
The absolute value function has a pointy spot. There's another one.
Birdie.
Mr. Birdie has a pointy spot. Anyway, so there's this function it's like how many pointy, it has every point on it is pointy.
Whoa.
And then you're like, bruh, how? How is it that every single point is pointy? Because like on the birdie, you have smooth, pointy, smooth. And if you try to make a function that's, okay, great, I got 2 pointies, but I had to have it be smooth between the pointies anyway.
It's
called
like a
important.
pointed star, like the fake stars that everyone shows. It's like that looking.
Fake star?
Like
the
like that thing, but like the pretty stars where they're all round pointy. Like the one you draw for sun when you don't know how to draw a sun.
Oh, like this?
Yeah, but pointier.
Even point, like a fractal. You can do it fractally. You can
Yeah.
do the fractal with you start with this shape,
Yeah, and
and then you keep adding more pointies to it, make it really prickly.
the infinite triangles.
Yeah, it's called. Anyway, the function pattern is called the wire stress
That
function.
proves that.
It's kind of related to it's kind of related to a fractal type.
Sweet.
Anyway, if I remember, I'll pull it up on the. I'm going to show you something on the computer in a few minutes. We'll pull it up and look at it. It's kind of neat. Okay. Anyway, you might look at this and go, huh? that guy he almost looks like a shrugging parabola or something, right? Like, actually though, what if I continued the pattern? Well,
Like a shrugging octopus.
Well, no, what I was trying to get at, I guess, isn't it the same structure as the sine function?
Yeah, what?
Just over one.
It's just shifted, it's actually shifted a distance of pi over 2, right? Because it's that distance. Or imagine shifting all these points over that much. Which I hope makes sense, because, I mean, think about the sine function. The sine function is talking about all these height values as you move around the circle. And the cosine is talking about all these horizontal values as you move around the circle. Well, it's all the same values, right? They just happen at different times, different positions.
Yes.
You okay, hand banana?
Yeah.
You sure?
Okay.
She needs more ions. I have some batteries in the,
Oh, that's one of my favorite.
so many ions in those things. Okay, so. Oh, here's a question for you. Think about it. Don't shout it out if you know it. Give everyone a chance to think about this one. There's a point right around here, right around there, where the y value is 1/2. This is a possible question you might be asked down the road slightly. What x value on this function would produce that y value? Well, that's not correct, but also don't shout it out if you don't know. So which of you guys think you have an answer for this one? Zach's pretty confident? Even if you're half confident.
Pi over 6.
Close, very close.
Yeah, that's the one.
That would have been the answer for the sine function.
Yeah.
So the sine graph has the point pi over 6, 1/2, and that's because, that makes sense? Because the sine of pi over 6 is 1/2.
I think I got it.
What's the answer, Nikita?
Is it pi over 3?
Pi over 3.
Yeah.
You guys see what I'm talking about? Okay, so you can ask that question a million different ways. Oh, where is this graph going to have a y value of √3/2? 5 or 6? Okay. Last one, tangent time. It's tangent time. Interesting. Okay, this graph's going to be a little weird. Thanks. So, as always, back to the unit circle. And we're going to go starting from the same position. The tangent of 0 is, keeping in mind that, again, don't mix up your x's and y's, but if you are talking about a unit circle and some xy position on the unit circle, the tangent is given to you by the vertical over the horizontal, right? SOHCAHTOA, it's the opposite over the adjacent. So the tangent at 0 is 0. Everyone's 0 over here. Okay, so my first point, when x is 0, y is 0. Are there any questions on that? Okay. Now, what the question you want to answer, let's just do it all at once here. What happens as we approach pi over 2? What happens to our tangent numbers? So if you want to be really precise, you might write a statement like, as your angle approaches pi over 2 from the right, or technically it's from the left, but as theta gets close to pi over 2, the tangent of theta is getting really big, at least in this quadrant, right? Does that make sense? So what that tells me is that this pi over 2 is going to be an asymptote. Do we understand that? Or is that confusing?
Yeah. Understanding.
So as our x value, our theta, our angle, gets closer and closer to pi over 2, 90 degrees, this is going to go zoop, like that. We sure there's no questions?
Can
For
you?
the original tangent value, would it not be tan 1 equals 0?
Tangent of, no, this angle is 0, right? 0 radians.
How?
You could say something, you could say a statement like, when cosine, right, this is where it gets confusing, because when I'm saying, when you're writing it this way, what you're really saying is my vertical axis value is equal to the tangent of some angle. But because we're always working on an x, well, we're typically working with an x and y axis, it's challenging because you have to really shift your thinking to go, well, in this graph, the x-axis is the angle values, and the y-axis is the tangents of those angle values. Whereas, like when you first run the unit circle, it's a totally different framework where your x value tells you the cosine and the y value tells you the sine. So that's it can be confusing to like really get that sorted out mentally. Taylor, do you have a question still? Sure?
Yeah.
Okay. What if we had gone the other direction? So I'm gonna rewrite this as a little bit of this is kind of sloppy notation, but I think it's okay because it kind of communicates. The reason it's sloppy is you're like, well, we'll get to this in a second, but what if you were on just the other side of pi over 2? Would you still be having positive infinity as your behavior? No. Before we get there, though, let's talk about what's going to happen on the left side here. Because maybe you have a feeling that, well, there's so much symmetry in this stuff that I have a feeling that there's going to be this symmetry here. Is that correct? Yes. Because what kind of tangent values do you have down in this quadrant? They're negative numbers, right? Still making sense? And as you approach here, so as you start approaching negative pi over 2, if you were going clockwise, you'd be approaching negative infinity for your tangent. So this graph goes swoop, like that. All right. We're about 70% of the way there. Can you take those marker stacks down? Thank you. Thank you. Okay.
AJ, I promise.
It was all AJ. Okay. I'm thinking it's going to repeat. So why does it repeat? Well, let's go back to this spot here. Right before we got to pi over 2, so right before our angle was at pi over 2, we had really large positive tangent values, right? Then we hit this asymptote, because the tangent of pi over 2 is undefined. But over on this side, what kind of tangent values do we have?
Very small.
They're very negative.
That's what I meant.
This would be huge negative numbers, right? It's the same kind of ratio we had over here, big vertical divided by small horizontal, right, opposite over adjacent. But over here it's negative, so what's going to happen is you're going to have like big negative values. And then as you travel around, what's the tangent of pi? Tangent of pi is 0. So you go from these big negative numbers, and you hit 0, and what kind of tangent values do you have in here? Positive, and they get really big as you approach as you approach 3 pi over 2. So you've actually, at this point, it seems as though we've kind of cracked the periodicity of this function, meaning it just repeated itself. Going from negative pi over 2 to pi over 2 is the same exact pattern as going from pi over 2 to 3 pi over 2. And then I'll spare you the thorough explanation, but I hope it makes sense to you why it would just be the same thing over here. Okay. So there's a lot of differences here. This function has a lot of differences from the other ones. Like, for example, what's the domain of this function? Not all reals, certainly. Anyone throw out a number that x is not allowed to be?
5 over 2.
Pi over 2. Plus or minus pi over 2. Plus or minus 3 pi over 2, ... Any half multiple of pi is going to be an issue, right? It's going to be an asymptote.
So the ... is acceptable here?
Yeah.
Okay.
Should we say x cannot equal this?
Oh, thank you, Brad. Yes. Sean Patrick, if you wanted to go for the full flex, you could go the set of numbers plus or minus 2n plus 1 times pi over 2, where n's an integer. I guess you don't even need the plus or minus if you say n's any integer. There you go. And you can really flex on them.
Okay, yeah, good.
Well, all that says is any odd number over 2 times pi.
Okay.
Because any odd number is an even number plus 1, right?
Uh-huh. Okay.
It's not that essential. The essential thing is you understand that, like, why does this function have an asymptote at pi over 2? Well, because the tangent is undefined at pi over 2, and you get very large tangent values as you approach pi over 2. Okay, what's the range? All reals. Everyone understand that? Going all the way from negative infinity to positive infinity. Lastly, the period. How big, how wide is one cycle of this function? Pi. That's kind of weird, right? It's only half as big. All right. I'm just going to end my video here. I'm going to show you something on the computer real quick, but all the millions of Twitch fans can